Okay, so here we are moving into chapter 2 now on energy and matter. Of course, chemistry is the study of matter, the changes matter undergoes, and the energy that accompanies those changes. So energy and matter is a pretty core concept, not only to chemistry, but to any of the natural sciences. There's pretty much nothing else in the universe aside from matter and energy. So that's what we tend to study in the natural sciences. The social sciences, where you're studying human interaction, then things get complicated. But natural sciences, it's simple, matter and energy. So in this subchapter video here, we're going to focus on energy. And energy is one of those things that we know it when we see it, but there's not a whole lot of ways to define it that are correct. So it's going to have sort of that vague definition that you might remember from middle school. But again, to be entirely accurate and to make the physicists happy, we've got to keep things vague with energy. So there it is, that relatively obscure definition that you probably have heard at least once or twice in your K-12 education, and that is that energy is the ability to do work. It's not a very tangible idea, but at least it's correct. The physicists don't get mad. We don't say anything incorrect when we use that working definition of energy. If we want to get a little more specific, we can classify energy as either potential or kinetic. And the energy, for instance, from the food we eat enables us to do the work we do. And again, we'll focus a lot on chemical potential energy. That's the stored energy in that food. And then the mechanical activities of our body that it allows us to do. Okay, so defining potential energy, that's the energy stored for use at a later time. It's also known as energy of position. You may have learned that back in your middle school or high school days. And so some examples here for potential energy is water behind a dam that's being held there against some potential that it could kinetically, it could move afterward. A compressed spring, the spring has that energy stored. It's not moving at that moment, but it's got that stored energy. Chemical bonds and anything, gasoline, coal, or food is what our author tends to focus on here in this chapter, but really chemical bonds store energy in any molecule. Some molecules have more energy stored in those bonds and make better foods and fuels. Other molecules have less energy and tend not to be as good for those uses, but all chemical bonds store energy, and we're the benefit of that energy release as our body slowly releases chemical energy from our food to allow us to use ATP as our energy currency and perform the functions, mechanical, muscular functions that we need to do each day. All right, so if potential energy is the stored energy, the energy stored in either bonds or springs or by virtue of being in a higher position, kinetic energy is the energy of matter in motion. So some examples here: swimming involves a lot of use of muscle and movement of the water. That dam was holding the water in our potential energy example. Now here in the kinetic energy, it's that water flowing over the dam and possibly, moving turbines being used for hydroelectricity, so on and so forth. Working out. Hopefully all of us work out at least a couple of times a week to use up some of those stored potential energy molecules that like to accumulate in the human body as fat, so working out helps to prevent too much of that from happening. Burning gasoline in your internal combustion engine, if you have a conventional engine car, that's a great example of kinetic energy. Okay, so because that definition of energy itself was so vague, let's take a moment here to pause for a learning check, see how we do on classifying each of these following as potential energy or kinetic energy. So A, rollerblading; B, a peanut butter and jelly sandwich that hasn't been eaten yet; C, mowing the lawn; or D, gasoline in the gas tank, not in the engine yet. So for each of those, hopefully you can identify it pretty simply as either kinetic or potential energy, and go ahead and pause the video if you need another moment, but otherwise we'll see how you did on your selections. Alright, so here we have them. A, rollerblading, right? That's body in motion, so that's kinetic energy. B, that peanut butter and jelly sandwich that we didn't eat yet, that's potential energy. Once you eat it and start to digest it, then we're going to convert that into kinetic. But the sandwich itself is a lot of great stored chemical potential energy. C, mowing the lawn, that's an active process and involves movement, and therefore kinetic energy is the classification for it. And then finally D, gasoline in the gas tank. It hasn't been combusted yet in the internal combustion engine, so that is still stored chemical potential energy. Hopefully you did well on those. If you're struggling, please continue to read the text, watch the remainder of these videos for Chapter 2, and then try some end of chapter problems, try your homework set problems. If you're still having trouble, of course, reach out to me for help. Okay, so heat, you may not have thought about it this way, but heat is also known as thermal energy, and it's associated with the motion of particles. So the higher the temperature, and temperature is a measure of the average kinetic energy in a sample, the higher the temperature, the faster those molecules are moving on average. And so, therefore, if the sample size is fixed, the greater the heat content. Adding heat to food increases the movement of the particles, makes the food hot, also can cook certain foods, right? An egg that's left out at room temperature doesn't do much, but if you heat that egg, you can denature those proteins, a subject that we'll talk much more about in Chem 142, but cooking of food is associated with chemical reactions that are enabled by the higher temperature of heating the food. So heat's an important part, especially if you're in the Binghamton area in the winter, right? Keeping the indoors much warmer than the outdoors is critical, and so that heat energy is involved with some sort of burning of stored chemical potential, some sort of fuel or some sort of electrical source of heat. And then that increases the average speed of the molecules, and we feel that as a higher temperature. Heat content is measured in joules in the SI system, or calories, which is what we're used to here in the United States. So it's important, obviously, in chemistry, like all the natural sciences, that we have a common unit. So the joule is the common unit. That's what the physicists use. The chemists have resisted. We still see calories from time to time, or kilocalorie, but really joule is where we need to be moving. So it's important to realize that 4.184 joules, capital J for the unit abbreviation, equals 1 little c calorie, and that's exact, so that's exactly 1 calorie, and we won't let that affect sig figs. So there we have our potential conversion factors, either the 4.184 joules in the numerator and the 1 calorie in the denominator, or the inverse of that. 1 kilojoule, obviously a definition using that kilo prefix, equals 1,000 joules, just like 1 kilocalorie equals 1,000 little c calories. Another thing you'll run into from time to time if you're looking at food labels is calorie with a capital C. Calorie with a capital C also means kcal, lowercase c. So food calorie, as it's sometimes called, as capital C cal, is really 1,000 little c calories, or 1 kilocalorie. So lots to be careful for with units here, as hopefully Chapter 1 got you thinking about those units. And here in Table 2.1, we see some energy comparisons for various resources. And if you look there, when humans are sleeping, we're not using a whole lot of energy, about 10 to the 5th energy in joules, which would be, again, something on the order of 10 to 50 kilocalories of energy, or capital C calories, food calories. So you're not burning a whole lot of those chips. If you eat a bag of chips before bed, you probably won't even have that calorie content burned off by morning. As we move up, we see the different energy amounts. And finally, up at the very top, energy radiated by the sun per second, 10 to the 26th. That's a lot of energy. And then even if we look down below, the solar energy actually reaching the Earth per second is much less, but 10 to the 17th is a big number. And it's one of the reasons there's the push toward the greater use of solar energy, because all of this energy is falling on the Earth all the time, and we're not making very good use of it. The plants are. They're doing a great job of capturing that energy. But as humans, we should really be looking into solar technologies to increase the amount of energy that we recapture from that solar energy that's just often lost here as it hits the Earth. Okay, so let's take a look. We'll pause for a learning check here, see how we're doing with this idea of energy and specifically the heat content of food. So for this example, how many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized? All right, so we've got it in joules. We want to convert it into calories. Hopefully you recall that conversion factor, which I would provide because it's going from a standard unit of joule to the non-standard unit of calorie. So that's, again, 4.184 joules equals 1 little c calorie. So with that value, hopefully you can set up your dimensional analysis and go ahead and solve the problem. Pause the video if you need another moment, and when you start up again, we'll look at the answer. Alright, so I lied. Before we look at the answer, let's make sure you're using that problem-solving strategy that we talked about before. So step 1, state the given and needed quantities and analyze the problem. So we're given the 150 joules of energy. We need to know how many calories that relates to. So then in step 2, when we make our plan to convert it, we go ahead and put that given unit of joules. We know that we need some energy factor. This is called dimensional analysis when you set it up so that your units will cancel to give you the desired unit. So we need an energy factor that's going to have joules in the denominator to cancel with the 150 joules in the numerator, and it's got to have calories in the numerator to give us a final unit of calories. Okay, so there we have it. We know that we need that relationship, 1 calorie, 1 lowercase c calorie equals 4.184 joules. And so we've got 2 possibilities for how we can make that into a unit factor. If we look at our joule that we're given, we know we need to have joules in the denominator, so we have to pick the variety that gives 1 calorie over 4.184 joules. So there in step 4, we can set up the problem to calculate the answer and to get the unit we desired. So effectively, we end up taking 150 joules and dividing by 4.184 joules. That 1 calorie up top is exact, but the 4.184 joules, we do consider those to be 4 significant figures. Since our 150 doesn't show the decimal place, we're assuming that there's just the 2 sig figs, the 100 and the 50. So in our final result, we should have just 2 sig figs because we apply the multiplication rules, division rules here, so that our final answer should have the same number of sig figs as our least significant value in the calculation, and therefore we get an answer of A, 36 calories. So hopefully that one was pretty straightforward. Go ahead, practice the homework set. If you still want additional practice, do the end of chapter problems. But if you're struggling with this and that's not getting any better as you do more problem solving, please reach out to me for some help. Otherwise, we'll close our subtopic of energy and pick back up with the next part of chapter 2 in the next video.